Okay, today we're going to be looking at the second half of hypothesis testing, so we're going to look at for means. So to hypothesis test regarding the population mean, we're going to use the following steps, provided that the sample is obtained using a simple random sample. Or, if that's not the case, it's from a randomized experiment. So you're going to have some sort of randomness in there. The sample has no outliers, and the population is it comes from is normally distributed. Remember, if there are it is skewed left or skewed right, as long as we have the sample size is large and is greater than or equal to 30, then we can use the following. Last but not least, the sample values are independent of each other. And remember this one, another way you can think about it is that it's less than that 5% of the population. So just like we had with our proportions, there's 3 different types of alternative hypotheses we can have. The null is always the same here, that our mean, so mu, is going to equal whatever mu we're looking at for our alternative. Mu we're studying. So our alternatives, if it's a two-tailed test, we'll still compare mu to the mu of our null, but a two-tailed test is going to be not equal to. A left-tailed will be less than, and a right-tailed will be greater than. Our significance level is going to be alpha, and remember this is depending on the seriousness of making a type 1 error. So as we go through, remember we're going to compute a p-value, and then we compare that to alpha to decide whether to reject or fail to reject the null hypothesis. If the p-value is less than alpha, reject HO, right? P is low, reject the HO, right? If the p-value is greater than alpha, fail to reject HO. So if we're looking at a two-tailed test, then we are looking to see what the probability, if that probability is less than kind of both of these. So these two tails would be alpha divided by 2 is going to be like the cutoffs. Whereas if you just have a left-tailed test, then we'd have our cutoff and we'd just have alpha there. Right-tailed, we'd have just the right tail, and that would be an area of alpha. In general, as long as you kind of remember, the pictures are not as important here, as long as you remember that the p-value has to be smaller than alpha for us to reject the null. And then finally, we're going to state the conclusion. All right, let's keep going then. There's something new here we're going to introduce, and this is the idea of practical significance. So we've been talking about, stating our conclusion, if there's statistical significance, but is it practical? So it's when the difference between the statistic and the parameter is statistically significant, but not large enough to cause concern or be considered important. So it's like, hey, we may decide to reject the null, but then as you actually look at it, it's like, oh, the data we found was really not that different from what we had. So our caution here is that when you have a large sample size, it can lead to results that are statistically significant, even though the difference is not enough to be considered practically significant. So larger n's leads to smaller p-values, even for small differences. Okay, let's go ahead and head into a hypothesis test. Last year, the government made a claim the average income of the American people was $33,950. However, a sample of 35 random people was taken recently and showed the average income was $34,076, with a population standard deviation of 324. Is the government's estimate too low? Conduct a significance test to see if the true mean is more than the reported average. So the first thing I want to check is simple random sample. And here it was stated to be a sample of 35 random people, so we're good there. The next thing is we either want to know the underlying population is normally distributed and there's no outliers, or we've got, so I'll just say maybe normally distributed. But in this case, since we don't know that, since we have n is greater than or equal to 30, right? Our n is 35. We're all set there. And last but not least, independence. And this kind of can go along with, too, that, like, you know, your n is less than or equal to 0.05 of capital N. Can also tell you independence, or it can just be assumed. In this case, I'd say, hey, just because you make a lot of money doesn't necessarily impact the next person. Or you could say 35 is definitely less than 5% of the population. So let's go ahead and state our null and alternative hypothesis. So our null here, we're talking about means. We're using mu, and it's always equal to for the null. And we were looking at that people make $33,950. Our alternative here, we're going to use the same mu and the same amount, but we want to know, is the government's estimate too low? So in reality, do people make more money? Be careful, just because it says low there, you may think, oh, I should do a left hypothesis test, left tail test. But since we're looking at, hey, too low, we're doing greater than. Okay, so here, our alpha is 0.05. So let's go ahead and find the test statistic. So we are going to start using, go over stat, go right to test. Remember, anytime we did means, remember like our confidence intervals, we did t, like a t interval for means. So here, for hypothesis test for means, we're going to use the t-test. So that's second one. So z for proportions, t for means in this class. Our mu is 3,950. Our mean of our sample is 34,076. Our standard deviation there is 324. And our n is 35. And we're looking at this is greater than. Okay, I do think it's always a good practice to kind of put down what you typed in, just in case you put something in the wrong spot. Then we could still give you some partial credit. Here, or let's say you like just misdid a number, like you changed the standard deviation, even though the only time we do that is with normal CDF. People sometimes want to do it here too. Not the case. We're doing greater than or equal to, sorry, mu is greater than, mu not, the null. Okay, so let's go ahead and hit calculate. So our test statistic is t in this case, and if we round up 3 decimal places, we get 2.301. And then we're going to look at our p-value. So our p-value is at 0.014. And it's nice here because it just gives us one p, because we're talking about means here, not like the p for the proportion and the p for the p-value. So since 0.014 is less than 0.05, which is our alpha, we reject the null, and then there is sufficient evidence to conclude, we're concluding that the government's estimate for average income is too low. I'll say of 33,950, average income is too low. Okay, let's go ahead and look at the next page then. Okay, the next one, the manufacturer of a daily dietary supplement claims that its products will help people lose weight. The company obtains a random sample of 950 adult males at ages 20 to 74 who take a supplement and finds their mean weight loss after 8 weeks is 0.09 pounds, with a standard deviation weight loss of 7.2 pounds. Test the hypothesis that the mean weight loss of 0.9 is significant using alpha is 0.01 level of significance. Okay, so here, our null hypothesis is, I would say, so we just want to look at if they have weight loss. So if they don't have weight loss, they're just going to stay at 0 pounds, right? No weight loss, hey, okay. Since we're looking at weight loss, there's kind of two ways we could do this. We could say loss is like negative, and then in which case we'd have mu as less than 0, and you'd have to do like a negative loss, etc. But I think it's going to be a little bit easier to leave things as a positive amount. So, hey, you lose 10 pounds, even though you're losing it, let's still call it positive 10, right? As far as our mean and standard deviation go. So a couple different ways to think about that. I'm going to assume mu is greater than 0, and we're thinking about the loss as a positive value. Right, so if you lose 10 pounds, we're going to call it 10. Okay, it gave us our alpha as 0.01. So let's compute our p-value. So once again, we're going to do a t-test. So stat, go right to tests. And we've got data here. Sorry, we've got statistics. So our mu naught is just 0. We're looking at, hey, does things actually differ from 0? Our mean here, we said the average weight loss is 0.9 pounds. With a standard deviation of 7.2. And N is 950 adults. And we're looking at keeping it greater, right? That you have more weight loss than that. Okay. So our test statistic would be that t, and then our p-value is really small. So 6.23 e to the negative 5 means 0.0000, and then the 6, right? You're moving the decimal places 5 to the left. So in this case, our p-value is really, really small. So it is going to be less than our alpha. So we reject the null and claim that there is sufficient evidence to conclude that like the supplement will help people lose weight. Okay, but let's actually look at this for a minute and actually consider. So, do you think the mean weight loss of 0.9 pounds is worth the expense and commitment of a daily dietary supplement? In other words, does weight loss have any practical significance? I would say probably here, especially what was this, 8 weeks? I'm going to say, no practical significance. Because losing 0.9 pounds in 8 weeks is not significant, right? You basically have stayed your same weight. I spelled significant wrong. Let's see. Significant. So it's probably not worth it. You could even lose that yourself just by walking every day, let's say. Okay. Test the same hypothesis that alpha equals 0.1 level of significance if n just equals 40 subjects. Assume the same sample statistics. If a sample mean weight loss of 0.09 is more than 0 pounds, what do you conclude about the impact of a larger sample size? So notice if I go back and I go to my stat, so I do the t-test again, and the only thing I change is n to be 40. So t-test, and then change n to equal 40. You'll notice now my new p-value is significantly larger. I get 0.217. So because of that, you'll notice here that our p-value is greater than alpha. So that means, 0.1 is what we use, not 0.5. So that would mean we failed to reject the null here. And we would conclude that there is not sufficient evidence, right? Failed to reject the null, and there is insufficient evidence. To conclude, the supplement will help people lose weight. So what do you see here about the larger samples? Just like we said before, in our notes, larger samples can lead to something, so they can lead us to have a statistically significant result. So they lead us to reject the null, even though the difference between our null and our statistic are not practically significant. So lead to statistically significant results that are not practically significant. Okay, we got one more example to look at together here. So every road has at some point construction zones that have much lower speed limits. To see if drivers obey these lower speed limits, a police officer has used a radar gun to measure speed in miles per hour. We got our simple random sample of 10 drivers in a 25 mile per hour construction zone. The officer notices the speeds were approximately normal. The reason why we're saying approximately normal, right, is because our sample size isn't larger than 10. So we need that condition to be true. The other one is randomness, which we have. And then the last one, remember, is independence, which is usually assumed. Or you could say is less than 5% of the cars driving on the road. Okay, we're going to perform a significance test with alpha equal to 0.10 and to see if drivers obey the speed limit. So, our null hypothesis here is that mu equals the 25 miles per hour. Okay, we just want to see if they obey the speed limit. You can take, some different interpretations here, but I'm going to go with the fact that, hey, if they're not obeying it, if you go too slow, it's obnoxious, and if you go too fast, it's obnoxious. So I'm going to go with mu is not equal to 25. However, I could also see an argument as to why you maybe want to do mu is greater than, etc. So let's go ahead, and this time let's do our t-test. Remember, as we look at our t-test, it asks you for two things. You can either use data or you can use statistics. I could go ahead and compute, the mean, the standard deviation, etc. for my data, or your other option is we can go to stat and go to L1, and I can input these data points. So I can do 27, 33, 32, 21. Oop. Oh, I'm not doing so well. 32, 21. 30, 29, 25, 27, and 34. Okay, so now we go stat, we go right to test, we're going to go to our t-test, but this time I can go over and use data. So I put this into L1. I'm going to use a t-test, and I use data this time. Okay, so the mu we're comparing it to is 25. We got our L1, our frequency is that, and we're going to say it's not equal to, and we're going to do calculate. Okay, the alpha they told us to use was 0.10. Our test statistic is that t-value, so 3.051, and our p-value is 0.013. Oh, we did round that up to 1.4. Okay, so here, since our p-value of 0.014 is less than alpha, which is 0.10, we reject the null and conclude there is sufficient evidence to conclude that drivers do not obey the speed limit. Okay, so in this case, which conclusion, based on giving your conclusion, which we said reject the null, which type of mistake could you have made, a type 1 or type 2? Tell your neighbor and tell what this mistake means in context. In this case, since you reject the null, even though the null may have been true, we made a type 1, or we could have made a type 1 error. And that would be saying, hey, we think people actually break the speed limit, when in reality they don't. Okay, that's it for 10.3. 10.4 is just reminding us, hey, look for keywords that indicate which one you're using, right? So anytime I have like a mean, I've got like standard deviation, right? Or I've got data values, you're going to be talking about a mean. This is like quantitative data, right? Anytime we've got qualitative data, when we're talking about proportions, etc., I wouldn't worry about these tests, but I would say, okay, know that anytime we're talking about proportions right now, you're going to use your one prop. In this case, we always do Z for proportions. So Z test. That's number 5 on your calculator. And then for means, we're always going to use number 2, which is your t-test. Since we have a whole day of review before your test, I did not give you a separate assignment on this, but I think it would be good for you to start kind of looking at these things. Okay, that's it for today. Good luck with your assignment.